All right, we're going to be asking a slightly different question than we've been used to asking in this video, and this is going to talk about how we find the area under some sort of function. So say we've got some region that's underneath a curve between two different points. Say we're going from some point A to some point B, and there is some sort of region between the x-axis and this curve, this function y equals f of x, that we would like to know the area between. So say we want to go ahead and find this area. We're going to call it this region S. Make sure this is clear that I'm talking about the region and not necessarily a point on the x-axis. So what is the area of S? Now, because S has a weird shape, we don't have a specific formula. So, no specific formula, at least yet. CIFIC. Since S has an odd shape, and so what we're going to do instead is we're going to actually just try to approximate or guess what the area is using something that we can easily find the area of, and that's rectangles. So of all the shapes we know, rectangles are the easiest, one of the easiest to find the area of. So we will approximate it. We'll approximate this area using rectangles. Alright, so if we're going to use rectangles, the question would become how we could go ahead and do that. So say we wanted to go ahead and use 4 rectangles to try to estimate the area under the curve of the parabola y equals x squared from 0 to 1. So say here's 0, here's 1, and we want to make some rectangles. Well, there's a couple of different ways we can do this, right? The two important things you need for a rectangle are the base and the height. So you need to know how wide the rectangles are, and you need to know how tall the rectangles are. Now the width we can easily figure out, right? If we want to use 4 rectangles, what we'll do is we will split the interval 0 to 1 into 4 intervals. That have equal width. And we're going to call the width delta x. And delta x will just be the endpoints, b minus a, divided by the number of them that there are, in this case, n. So here, when we say we have the interval 0 to 1, this is the interval a to b, kind of like we had talked about up in this example. And now we know that we have 4 of them, so that will be our n, how many we have. So that'll be 1 minus 0 over 4, or in other words, our width will be 1/4. So the hard part is then trying to figure out what the height is going to be of each of these rectangles. So there's a few different ways to do this. We're going to discuss 2 of them here, but then we'll get into a third as we keep going. So let's say we wanted to use the right endpoints. All right, so say we've got this interval, these 1/4 wide rectangles. We start at 0. We'll get to 1/4, 1/2, 3/4, and then 1. Not exactly drawn perfectly. But let's say we want to use the right endpoints. So that means that if our first rectangle is going from 0 to 1/4, the right endpoint will be whatever the function value is at 1/4. So that'll be f of 1/4 as the height. And so that'll give us our first rectangle. We then would go over to the next the next rectangle from a fourth to a half, and on the right hand side of this is a half. And so the height of the function there will be whatever f of 1/2 is. And so we'll use that to make our next rectangle. Then if we look at our next interval, we're going from a half to 3/4, so we'll use the right endpoint again. And the height of this rectangle will then be f of 3/4. And then last but not least, our last rectangle goes from 3/4 to 1. So we will go ahead and use f of 1 as the endpoint for that rectangle. Use that to determine the height. So here, if we want to go ahead and estimate it using 4 rectangles using the right endpoints, this will be 1/4 times f of 1/4, I added one too many parentheses there, plus 1/4 times f of a half, plus 1/4 times f of 3/4, plus 1/4 times f of 1. Or in other words, this will be, since this is 1/4 times all of them, we can factor out the 1/4, and we'll get 1/4 times f of 1/4, which will be 1/4 squared, plus f of a half, which is 1/2 squared, plus f of 3/4, which will be 3/4 squared, plus f of 1, which will be 1 squared. And so we add all these up, divide by 4, and what we get for the area is 0.46875. So notice what this is going to do here. When we're using these right endpoints for this function in particular, is this is going to give us a little more than the area under the curve, right? The area under the curve would be kind of just this part that's under the curve, but we get a little bit extra here. So this one, this seems to overestimate the area for this function. Okay, well, what's an alternative? Well, instead of using the right endpoints, we could just use the left endpoints instead. So let's try that. Let's use our left endpoints. All right, so again, we're going to have the same bounds on our intervals. They'll all be 1/4 wide, so we'll go 0 to a fourth to a half to 3/4, and 3/4 to 1. But if we're on this first interval, if we're using the left endpoint, we're going to be using f of 0, and so this will just be that tall. For our next interval, we'll use f of 1/4 to give us the height of the rectangle. For our next rectangle, going from a half to 3/4, we'll again use the left endpoint, which will be f of a half. And then for our last rectangle, we'll use f of 3/4 to give us the height of the rectangle. So now if we're going to use 4 rectangles and we're using the left endpoints, we'll denote this estimate as L sub 4. So the big L means we're using left endpoints. The 4 means that we have 4 rectangles. And so again, this will be 1/4 times our f of 0, maybe I'll use square brackets instead, plus f of 1/4 plus f of 1/2 plus f of 3/4. And if we're getting all these different function values, all we're doing to get each of those, because we're looking at x squared as our function, is we're just squaring whatever the value is for x. So 0 squared plus 1/4 squared plus 1/2 squared plus 3/4 squared. And all of this, of course, is times a fourth. So this is 0.21875. And what you might notice about this, one, it's a different number than what we got here. Again, these are just estimates. But all these rectangles are underneath our function. So this seems to underestimate the area. Okay, well, great. So that means we know that whatever this area is going to be between 0.21875. That'll be less than the area. And it'll be less than 0.46875. So our area has to be between both of those. But do you think we're going to be happy with just having a couple of bounds, some sort of way to sucker that area in and say it's between those things? No, we can do better than that. We can try to get something that's a little bit better. Maybe we can narrow it down some more. But before we talk about how we'll do that, let's make sure we understand some notation. So here we used left and right endpoints. And so we had different ways of denoting how we were going to do that. So let's start with assuming. So let's assume F is on the interval A to B. And we want to find the area under it. The width of our rectangles will be found as delta x, which is b minus a over n. So here, b minus a, the left endpoint minus the right endpoint, divided by n. So this will be the length of the interval that we have divided by the number of rectangles that we'll be using. Now, we can use different types of endpoints when we're doing our work. So if we say we're using R sub n, we're going to have n rectangles, and we will use right endpoints. L sub n will be using left endpoints to figure out the heights of our rectangles. The last thing we can do is something called M sub n, which is try to use some sort of midpoints. In every single one of these, because we're using that little subscript n here, we're going to have n rectangles. So we just said that we wanted to make that interval a little bit tighter, right? We wanted to get a little bit better of an estimate. Well, what we're going to do is we're going to try to use a larger number of rectangles and see what sort of things happen. So say we used 10 rectangles. Well, if we use 10 rectangles and use right endpoints, we get 0.385. And if we use 10 rectangles and we use left endpoints, we get 0.285. So that shrinks our interval, right? We're getting a little closer. But we can do better than that. What if we used 30 rectangles? So if we use 30 rectangles and right endpoints, we get 0.3502, and if we use left endpoints, we'll get 0.3169. Now we're getting smaller and smaller with that chance to miss what we're looking at here. But overall, we can kind of see the trend, right? More rectangles gives us a more accurate estimate. Alright, so here's a nice little thing we can then take advantage of. The area A of the region S that lies under the graph of some continuous function is the limit of the sum of the areas of the approximating rectangles. In other words, that area will be the same as the limit as n approaches infinity of using the right endpoints for the area, which will be the same as the limit as n approaches infinity of using the left endpoints to determine the height, which will be the same as using an infinite number of rectangles where the midpoint is used to determine the height. Right, so we have all these different ways that we could go ahead and try to find that area, and if we use more and more rectangles, we're going to get closer to actually getting the value of the area. And if we were able to use an infinite number of them, that'd be pretty cool. Problem is, if we divide by infinity, we should get something that looks a lot like 0. So what's going to happen there? Okay, well this is going to kind of refresh us of the fact that all of our conversation on limits exists. So let's say we had that region we were looking at in the first example. What we want to do is we want to show that the sum of the areas of the upper approximating rectangles is approaching 1/3. So, okay, how do we do that? Well, what we're going to do is we're going to say that we have the interval 0 to 1 with n rectangles. Our delta x will be 1 minus 0 over n, or just 1 over n, for the width of all rectangles that we're using. And if we're going ahead and using the right endpoints, then that means we are using 1 over n times each of these different function values. So we'll be using f of 1 over n plus f of 2 over n plus f of 3 over n, and we'll continue that all the way up until we get f of n over n, which of course this is going to just be 1, but I'm going to write it as n over n just for sake of simplicity. So what this means then is that we will have 1 over n times 1 over n squared plus 2 over n squared plus 3 over n squared, all the way summed up to n over n squared. Now what we can do is we can pull out an n squared from each of these. So we end up with 1 over n times 1 over n squared times 1 squared plus 2 squared plus 3 squared, all the way added up to n squared. Now, this is where a little bit of a trick is going to come in. When we look at this, and this is something you probably wouldn't quite have guessed on your own, if we add up all the numbers from 1 to n, and we're squaring them, 1 squared plus 2 squared plus 3 squared plus da-da-da-da-da plus n squared, this is the same thing as n times n plus 1 times n plus 2, all divided by 6. Oh, sorry, not n plus 2, 2n plus 1. Don't know where my brain's at today. And if you're wondering, where did Mr. Smith pull that out of? This is something that is involved in sequences and series, which if you ever take a Calculus 2 class, you're going to get to learn a lot more about. Alright, so with all that being said, we can use this formula to replace all this. So we'll get 1 over n cubed, so n cubed is just from taking n times n squared, multiplied by n times n plus 1 times 2n plus 1 over 6. Which, if we cancel out the n with one of the n's down here, what we should get is n plus 1 times 2n plus 1 over 6n squared. Okay, well, how does that help us? Well, what we wanted to do is we wanted to take the limit of this as n approaches infinity. So what we'll do is we'll take the limit as n approaches infinity of this using the right endpoints to find the area, which will be the limit as n approaches infinity of n plus 1 times 2n plus 1 over 6n squared. Now, if we multiply those things in the numerator together, what we'll get is that we're doing the same thing as taking the limit as n approaches infinity of 2n squared plus 3n plus 1 over 6n squared. Now, if you remember anything about your limits to infinity, the thing that's going to happen here is we're going to actually be comparing the coefficients of the highest power terms in the numerator and the denominator. Since they match, the limit will be 2 over 6, which is the same as 1 over 3. So we end up getting 1/3 as our area. And it took quite a lot to do, right? It took us knowing the limit definition. It took us knowing this extra thing with series. It took us knowing how to figure out this area. There's a lot of things going on in this particular example. And we also haven't really talked about this series thing. So that's probably not the way we're going to be solving these overall. We'll probably have a little bit better of a way to do this. But in the meantime, let's continue looking at this idea of trying to estimate the area using these rectangles. And let's try it with midpoints. So we kind of alluded to the fact that you could use midpoints, but we haven't actually talked about how that would work in practice. So say we've got a region lying under the graph f of x equals cosine of x between 0 and pi over 2. So let's graph that really quick. Cosine is going to start at 1 when x is 0, and by the time we get to pi over 2, it's going to become 0. We want to estimate the area by taking sample points to be the midpoints and using 4 subintervals. So when we're trying to figure out delta x, this part won't change for any of the problems. This will be pi over 2 minus 0 divided by 4. In other words, each interval will only be pi over 8 in width. Now from here, we want to find the midpoint of each of these rectangles. So for the first midpoint, the interval is 0 to pi over 8. Start at 0, we end at pi over 8. To find the midpoint, we'll take 0 plus pi over 8, and we'll divide that by 2. In other words, we'll get pi over 16 for the midpoint. For our second midpoint, our interval is going to be pi over 8 to pi over 2 pi over 8, or pi over 4. Which means then that our interval midpoint should be pi over 8 plus 2 pi over 8 over 2, which will be 3 pi over 16. So what we're going to do is we're really looking at, when I go from the first midpoint to the next midpoint, I'm going to add a whole length of my interval. In other words, this is the same thing as adding pi over 8 in between each of these. So if we need to find our new midpoints, we're going to increment each new one by pi over 8. So that means the third midpoint will be 3 pi over 16 plus pi over 8, or 3 pi over 16 plus 2 pi over 16, or in other words, 5 pi over 16. And the fourth midpoint will be this 5 pi over 16 plus pi over 8, which will be 7 pi over 16. So what are we doing in essence? Well, we're taking and dividing this into 4 intervals. So here's pi over 8, here's pi over 4, here's 3 pi over 8, and we're going to use the height of the rectangle from the midpoint. So this will be pi over 16, this will be 3 pi over 16, we've got 5 pi over 16, and we have 7 pi over 16. And so this will be how we choose the height. So whatever the function value is there is how we'll pick the height for the entire width of the rectangle. So then here we'll go find the midpoint. And so notice how this is a little bit above and a little bit below. So that's really nice. We want it to be as close to the area as we can, and being a little above and a little below should help. Right, so this is our function, remember, y equals cosine of x. So that means when we're going to find the area with the midpoints, this will be m sub 4, and this will be pi over 8, so our change in our width of our intervals, times f of pi over 16 plus f of 3 pi over 16 plus f of 5 pi over 16 plus f of 7 pi over 16. And so this is the same as pi over 8 times cosine pi over 16 plus the cosine of 3 pi over 16 plus the cosine of 5 pi over 16 plus the cosine of 7 pi over 16, and this will give us approximately 1.006 as our estimated area. Okay, so we've got an estimate. Great. And it looks like it's a little bit above and a little bit below. That doesn't mean that it'll be perfect estimate, but it does mean that we should get close. All right, let's do one more example. Over a 30-second time interval. What we're going to do is we're going to take speedometer readings every 5 seconds, convert them into feet per second, and record those. So we've got these as our different times, we've got these as our different velocities, and so let's say we want to know how far we've driven. So our distance driven over the first 5 seconds, and this is of course assuming the speed was constant at 25 feet per second, would be 25 feet per second times 5 seconds. The seconds cancel, and we end up getting 125 feet. So say we wanted to estimate the distance that we drove over the entire 30-second interval. Well, what's hard for us is we don't necessarily know if we should be using the left endpoints or the right endpoints here, right? If we assume that the speed was 25 feet per second, then over that interval we drove 125 feet. But if we use the 31 feet per second over that 5 seconds, then we'd end up with 31 times 5, or 155 feet per second. So we've got different distances here. And so if we want to estimate, if we used left endpoints, what we'd guess for the total distance would be 25 times a 5-second interval plus 31 times a 5-second interval from 5 to 10 plus 35 times the 5-second interval from 10 to 15 plus 43 times the 5-second interval from 15 to 20 plus 47 times that 5-second interval plus 45 times the last 5-second interval. And this 5-second interval is going from 25 to 30. We don't have a 5-second interval after the 30, so if we're using the left endpoints, this is where we stop. And if we multiply these and add them together, we'll get 1,130 feet as our estimate. However, if we wanted to use the right endpoints, to create our estimate, our total distance would then be used by taking the right-hand side of each of these intervals. So from 0 to 5, we'd use 31. From 5 to 10, we'd use 35. And we'd keep going until the last interval from 25 to 30 would be 41. So now we'll use 31 times 5 plus 35 times 5 plus 43 times 5 plus 47 times 5 plus 45 times 5 plus 41 times 5. And if we do this, our estimate ends up being 1,210 feet. So we don't know the exact distance. We do know that our distance should be between 1,130 feet and 1,210 feet. So this gives us some sort of way to kind of bound what we think the total distance is between these points. Now, on the last page of these notes are 3 exercises where I'm going to ask you guys to try coming up with and creating these intervals on your own. So we've got R5 for this function on this interval, L3 for this function on this interval, and M4 for this function on this interval. So hopefully at this point in the notes you knew this means right endpoints and you want 5 of them, this means left endpoints and you want 3 of them, and this means midpoints and you want 4 of them. The solutions to this are going to be posted on Blackboard, so do look at the last page, and if you have any questions, do ask about them on the discussion board.